Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Basavakalyan. Now the 54th session of Graph Theory 2. The title of the topic is Eulerian digraphs. As we have got Eulerian graphs in the undirected graphs. Okay. Similarly, we have got Eulerian digraphs. Euler's digraph. So, what is the Euler's digraph? That we will see in detail. Euler's digraph can be identified in digraphs also. As in case of undirected graphs, Eulerian graph is also identified in digraphs also. In case of undirected graphs, a graph is said to be Eulerian if there is an Eulerian cycle. Also, we have got the characterization for the Eulerian graph in the undirected graphs. A graph is Eulerian if and only if degree of every vertex is even. Okay, but here in the concept of directed graphs, degree we cannot say simply degree. We will say we used to say degree, in degree, out degree. So the concepts are a little bit different. Okay, so what is that Eulerian digraph? That we will see. Eulerian digraphs can be identified, as I said, in directed graphs also. So what is that Eulerian graph? We will see. Before that, how we have defined Eulerian cycle in case of undirected graphs. Here we will see Eulerian line. Okay, instead of saying Eulerian cycle, we used to say Eulerian line, or you can say Euler's line. What is that? A closed directed walk which traverses along every edge once, and only once is called a directed Euler's line. So there also we are tracing every edge exactly once in case of undirected graphs. So here also what we are going to say, a closed directed walk which traverses along every edge once and only once is called a directed Euler's line. Okay. So now what is the Euler's digraph? As we have got a graph containing Eulerian cycle is called Eulerian graph. In the same fashion, a digraph which contains a directed Eulerian line or directed Euler's line is called an Eulerian digraph. Okay. So now we will see some examples. So in the figure 7, so you can see Euler line of a of the directed graph G. It is shown. So just let me see. A closed directed walk. You can observe a closed directed walk A, B, C, D, E, F, G. See, you can see A, B, C, D, E, F, G. So identify those edges. So it is A, B, C. Is it C? I think. Okay, let me once again. Okay. It is A, B, C. I think this would be D. Where is that D? Let us identify. Let me zoom if it is possible. Okay, I hope you will see this. So you can see A, B, C. Then where is D is a question. Where is D? I think it is A, B, C, D, E, F, G, H. A is given, B is given, C. Okay, where is D? That D is, yes, let me see this one. So it is, there is a loop. Okay, I didn't see this properly. So this edge A, B, C, this loop D. Okay, next E, F, G, H, like this. So we have reached the point with the P1. Okay, so this is the closed walk. Let me once again repeat. We have started at P1. So P1 to P2 in the direction, okay, towards P1 to P2. So this is the edge A. Next B, C, then one loop is there, D, E, F, G, H. Okay, so this is the, what we can say, Euler's line. Okay, a closed directed walk A, B, C, D, E, F, G and H which traverses every edge once one and only once, is an Euler line of the digraph G. So this is the Euler line which we have specified right now. Okay. So you know already the definition of Euler digraph. Any graph which contains Euler line is called Euler's digraph. So therefore the digraph G is also Euler's digraph because it contains Euler's line. Okay, so in the graph we have identified Euler's line. That's why what we said, the graph contains Euler's line. So this is a digraph which contains Euler's line. Any graph, any digraph which contains Euler's line is called Euler's digraph. So the given example is an example of Euler's digraph. Okay. So don't compare the degree of every vertex even or like that as that of the undirected graphs. Of course, similarity is there here also. So what we can say, there is one remark. Euler's digraph is strongly connected. However, conversely it is not true. You know, there are different types of connected digraphs. One is strongly connected. Next, you know, another one is unilateral, and one more is weak or weakly connected digraphs. Okay, weakly connected semi path. Next, unilateral, one way, one path from one vertex to another vertex. And the strongly connected digraph is from one vertex to other vertex, from that vertex to again from the previous vertex. There are two different paths. Okay. So what you can say, we have started at P1 and in this way we have traversed and we have reached. It implies it is strongly connected. So though we said it is strongly connected, but conversely is not true because there must be two different paths. Like that if you think, so converse part may not be true. Okay. So now what would be the characterization for Euler's digraph? As we have characterization for Euler graph, the degree of every vertex is even in case of undirected graphs. Similarly, what would be the characterization for Euler digraphs? So the characterization is given. A digraph D is an Euler's digraph if and only if G is connected and in degree of a vertex must be equal to the out degree of a vertex for every vertex V in G. So like there, degree of every vertex is same. But here we can't say degree of every vertex is same. What we are going to say, you choose any vertex of the digraph. The in degree of that vertex must be equal to the out degree of the vertex. It is for every vertices or every vertex. Then that graph will be Euler's graph. So it is a general result. Okay. A digraph G is an Euler's digraph if and only if G is connected and the in degree of vertex is equal to the out degree of the vertex V, and it should be for every vertex in J. So now we try to prove the result. So the number of times the walk enters a vertex is the same as the number of times the walk leaves the vertex. If you observe the previous diagram where we have given the example now, there you can see the number of times the walk enters a vertex or into a vertex, then it will be out of that vertex again, is the same as the number of times the walk leaves the vertex. So what we can say, into and onto, so from that vertex. Okay, so that is what we can say, into the vertex and onto the vertex, out of the vertex. Instead of saying onto, we can say out of the vertex and into the vertex. So like that, the number of times the walk enters a vertex is same as the number of times the walk leaves the vertex. So therefore, the in degree of every vertex is the same as the out degree of the vertex. So therefore, what we can say, the degree of a vertex which is out degree is always equal to the in degree of the vertex V. Okay, so now this holds for every vertex, has the result. So if you consider an Euler's graph, then definitely every vertex, if you consider every vertex of a digraph D, then the in degree is always equal to the out degree. So one part we have proved. So let us consider the other one. Okay. If you consider the in vertex of every degree is equal to the out vertex of the degree, then what you can say? You can say definitely it will be an Eulerian digraph. Okay, so therefore the simple result with a simple proof. Okay, a digraph G is an Euler's digraph if and only if G is connected and in degree of V is equal to out degree of V for every vertex V in G, then definitely it will be an Eulerian digraph. So how to prove the result? First part you have to consider it is an Euler's digraph. Then you have to prove the in degree is equal to the outer degree of that vertex. Similarly, if you consider the converse part, suppose the in degree is equal to out degree for every vertex V, then you must prove it is an Euler's digraph. Okay, so this is a simple proof which we have considered. So therefore, the result what we have considered in this session is Euler's digraph, the concept, and we have discussed what is the characterization for Euler's digraph with a simple proof. So with this we conclude this session. Okay, thank you.